Welcome to today's paper reading. Today's paper is titled SelfCheck, Using LLMs to Zero-Shot Check Their Own Step-by-Step Reasoning. This paper was published on AR14 by Ning, Miao, and colleagues from the Department of Statistics at the University of Oxford. Recent advancements in large language models, LLMs, have introduced chain-of-thought prompting, enabling stepwise reasoning to answer questions. However, these models struggle with nonlinear problems. To tackle this, the authors propose SelfCheck, a zero-shot verification schema designed to recognize errors in LLM reasoning without external resources. This schema uses weighted voting on multiple solutions to enhance question answering performance. Evaluated on datasets GSM-8K, MathQA, and Math, SelfCheck successfully identifies errors and improves final answer accuracies. SelfCheck is a novel zero-shot step-by-step checker designed to identify errors in the reasoning chains of large language models. Unlike existing methods, it does not require additional training data or domain-specific exemplars. The key mechanism involves a multi-stage approach where each step in the reasoning chain is checked by regenerating it independently and comparing it to the original. This method ensures that errors are decorrelated between the generation and checking stages. Evaluations on 3 math tasks show significant improvements in final answer accuracies and a reduction in incorrect solutions when filtering out low-confidence answers. In the context of large language models, LLMs, several approaches have been explored to verify the correctness of reasoning steps. One category involves few-shot verification, where methods like self-verification, SV, by Whye et al., 2022, and deductive verification, DV, by Ning et al., 2023, are used. However, these are often limited to specific tasks or formats. Another approach involves using external resources, such as symbolic logic solvers by Liu et al., 2023, or external databases by Ping et al., 2023, but these are constrained by the availability of such resources. Lastly, some methods involve training or fine-tuning a separate verifier model, as seen with the fine-tuning of GPT-3 on GSM-8K by Kabi et al., 2021, the training of a binary classifier by Li et al., 2022, and the fine-tuning of GPT-4 on a large dataset by Lightman et al., 2023. These methods, unlike SelfCheck, require additional data and computational resources. Figure 1 illustrates an example of using SelfCheck to verify a specific step in a reasoning chain, focusing on step 5. The process involves 4 stages: target extraction, information collection, step regeneration, and result comparison. In the target extraction stage, SelfCheck identifies that step 5 aims to complete the square. The information collection stage confirms that step 5 directly relies on step 4. During the step regeneration stage, the LLM independently completes the square using only step 4 as context, resulting in a circle with center 3, 0, and radius 3. This differs from the original step 5, leading the result comparison stage to conclude that step 5 is likely incorrect. After checking all steps, SelfCheck aggregates the results to form an overall confidence score, W. SelfCheck is a general-purpose, zero-shot checking schema designed to identify errors in the step-by-step reasoning of large language models. It operates by examining each step of a solution produced by an LLM and determining its correctness based on preceding steps. This is achieved by utilizing the generative modeling capabilities of the LLM, rather than directly asking it to check its own reasoning. The results of these checks are aggregated into a confidence score, which can be used to enhance predictive performance through weighted voting on multiple solutions to the same question. The process of step checking in the reasoning process is highly context-dependent. Each step must be evaluated based on its specific context and the preceding steps. The first stage involves target extraction, where the LLM identifies what each step aims to achieve. This is crucial for ensuring the regeneration stage proceeds in the correct direction. The second stage is information collection, where the LLM filters out irrelevant information, focusing only on what is directly related to the current step. This simplifies the regeneration process. The third stage is step regeneration, where the LLM attempts to achieve the step's target using only the collected information. This stage is less challenging due to the clear target and simplified context. Finally, the result comparison stage involves comparing the regenerated step with the original. If they match, it suggests the original step is likely correct. This method helps reduce the correlation between errors in the original and regenerated steps, enhancing the reliability of the checking process. The integration function Whye is designed to calculate a confidence score, W, for the overall correctness of a solution. The function takes as input a vector R0, R1, Rn, where each represents the result of checking step I. These results are encoded as -1 for contradict, 0 for not directly related, and 1 for support. The function uses a sigmoid transformation to compute W, which is a soft approach to verification, allowing for imperfect checks. The resulting confidence score is used as a weight in voting between different possible solutions, thereby increasing the accuracy of the LLM's answers. The experiments evaluate SelfCheck on 3 math reasoning datasets: GSM-8K, MathQA, and Math. GSM-8K contains 1319 samples, MathQA has 2,985 samples, and Math includes 5,000 test samples. These datasets differ in their structure and problem types. For instance, MathQA provides multiple choice options, while GSM-8K focuses solely on arithmetic problems, and Math covers a broader range of topics including geometry and algebra. The experiments use GPT 3.5 and GPT 4 as the language models, with a focus on GPT 3.5 due to budget constraints. The same prompts are applied across all datasets without any specific tuning. The performance of SelfCheck is compared with majority voting in Figure 2. Both methods show similar trends in accuracy increase with more generated solutions, but SelfCheck achieves higher accuracies due to weighted voting. When compared to deductive verification and self-verification, SelfCheck shows higher relative performance gains despite using in-context learning. Experiments with GPT 3.5 and GPT 4 reveal that SelfCheck significantly increases accuracy, with GPT 3.5 often performing well as a checker even against GPT 4 generated answers, indicating that using different LLMs can help reduce correlated errors. Figure 2 illustrates the performance gains of using confidence scores from SelfCheck for weighted voting compared to baseline methods. The upper plots demonstrate that the accuracies of both SelfCheck and majority voting increase as the number of generated solutions per question rises, reflecting the variance reduction from averaging over more solutions. The lower plots highlight the accuracy differences between SelfCheck and majority voting, including standard errors. Notably, SelfCheck achieves significantly higher accuracies across all solution numbers per question by assigning higher weights to correct solutions. Additionally, the improvements of SelfCheck surpass those of deductive verification and self-verification in their reported settings, despite the use of in-context learning from additional examples. Table 1 illustrates the significant performance gains achieved by SelfCheck when compared to majority voting, MV, across different datasets and GPT models. The table shows that SelfCheck enhances final answer accuracies even when only 2 candidate solutions are available per question. The performance gain, increment ACC, of SelfCheck over MV is indicated, with the standard error noted. The symbols and represent the proportions of questions with 0, 1, or 2 correct solutions, respectively. Notably, the gains from SelfCheck are typically larger in scenarios where it is common for only one solution to be correct, as these are the cases where weighted voting can significantly influence the final answer. The table also highlights the use of both GPT 3.5 and GPT 4 for generation and checking, demonstrating that using different LLMs can help to decorrelate errors and improve results. SelfCheck uses a confidence score to predict the correctness of a single solution. By setting a threshold T, solutions with confidence scores W greater than or equal to T are classified as correct. This method not only serves as a confidence score calculator but also significantly improves the performance of voting. When compared to majority voting, SelfCheck demonstrates higher accuracy across datasets such as GSM-8K, MathQA, and Math. Additionally, ROC curves show that SelfCheck provides meaningful control over true positive and false positive rates, unlike GPT 3.5, which lacks such control. Figure 3 illustrates the effect of increasing classification thresholds on the accuracy of predicted correct solutions across different datasets. For GSM-8K, the proportion of real correct solutions and predicted correct solutions rises from 67.5% to 76.5%. Similarly, for MathQA, this proportion increases from 59.4% to 82.2%. In the case of math, the increase is from 34.6% to 50.8%. This demonstrates that as the threshold for classification is raised, the likelihood of correctly identifying actual correct solutions increases, albeit at the potential cost of misclassifying some correct solutions as incorrect. Figure 4 presents the ROC curves for each dataset, illustrating the relationship between true positive rates, TP, and false positive rates, FP, as the classification threshold, T, is varied. As a comparison, directly prompting GPT 3.5 to verify whole reasoning chains results in no meaningful control on the false and true positive rates, FP and TP. Specifically, on the math dataset, both FP and TP remain at 100%, and on GSM-8K, they are 98%, as observed by Ning et al., 2023. This indicates that the checker always predicts the answer as correct, providing no useful information for filtering incorrect solutions. In this section, we conduct ablation studies to validate the key design choices of SelfCheck and to gain insights into its operational behavior. Due to budget and time constraints, all experiments are conducted on a subset of the MathQA test set, specifically 100 randomly selected questions. The primary objective is to evaluate the effectiveness of SelfCheck, understand the impact of its design choices, and identify areas for potential improvement. Majority voting is a method used to increase the accuracy of final answers by aggregating multiple solutions. However, this effect reaches a saturation point, as shown in Figure 5, where the accuracy does not exceed that achieved with n equals 9 solutions. In contrast, SelfCheck continues to improve in accuracy as the ensemble size grows. SelfCheck works by adjusting the weights of incorrect solutions, thereby increasing the likelihood of selecting the correct answers, even when their generation probabilities are low. This allows SelfCheck to effectively correct biased beliefs within the ensemble, providing a clear advantage over majority voting in terms of performance and computational efficiency. Figure 5 illustrates the performance of SelfCheck compared to majority voting in large ensembles of solutions. It shows that SelfCheck significantly outperforms majority voting in terms of final answer accuracies. Notably, the accuracy of majority voting saturates at n equals 9, never surpassing the performance achieved by SelfCheck with smaller ensembles. Conversely, the performance of SelfCheck continues to improve as the ensemble size increases. This is attributed to SelfCheck's ability to lower the weights of incorrect solutions, thereby increasing the likelihood of selecting correct answers, even when their generation probabilities in the generator LLM are low. This capability allows LLMs to effectively correct their own biased beliefs. In the ablation studies, the first comparison is between global and step-by-step checking. The global checker often incorrectly outputs correct, leading to final answer accuracies close to majority voting and a verification accuracy of 55%, only marginally better than a random guess. This highlights the necessity of step-by-step checking. Next, the study compares single-stage versus multi-stage step checking. Single-stage checking is better than global but still significantly worse than multi-stage, indicating the challenge of single-stage checking and the need for multi-stage decomposition. Finally, the study justifies the choice of regeneration and comparison over direct error checking. Even with a detailed example, direct error checking performs worse than the regenerate and compare approach, supporting the argument that LLMs are better at generation than error checking. Figure 6 illustrates the generation accuracies of various variants of SelfCheck on the MathQA dataset using GPT 3.5. The key findings show that the multi-stage step checking method of SelfCheck significantly outperforms the single-stage approach. Additionally, the global checking method, which does not consider steps, has accuracy levels very similar to majority voting, indicating its limitations. The error-checking method, particularly when enhanced with one-shot learning, demonstrates improved performance over the zero-shot version, further validating the necessity of detailed step-by-step analysis and comparison in the SelfCheck framework. Table 2 presents the verification accuracies of different variants of SelfCheck on the MathQA dataset using GPT 3.5. The accuracies are averaged from true positive and true negative rates. The SelfCheck method achieves the highest accuracy at 66.7%, followed by the error check, one shot, at 64.2%. The global check method has the lowest accuracy at 55%. These results highlight the effectiveness of the SelfCheck approach in comparison to other methods. The SelfCheck scheme introduced in this paper is a general-purpose, zero-shot, step-by-step checking method for large language models, LLMs. Unlike previous methods, SelfCheck does not require any additional data or external resources. Instead, it uses the LLM itself to identify errors in its reasoning through a novel regenerate and compare approach. By leveraging the results of this checking to perform weighted voting over different solutions, the scheme is able to significantly increase the final predictive accuracy of the LLM. This approach not only enhances error identification but also improves the overall performance of the model. Thank you for watching.